So in this example, I have talked about what happens when the player one and player two is unsure about this, the payoff structure of his opponent. So when we look at that, well, this is the like player one's type one, right? It's like and this is a type one of player two, and this is the type two of player two. Okay. So as I mentioned before, when the player once receives a signal, then he is able to know what the signal means, meaning that what is the type of the player one, but he does not, like P1, does not have any assurance about the type 2. Okay, so in this case, obviously the question is, okay, what is the strategy? Okay, that should be what? Uh, that should be something like B B, comma B S. I mean, this is one of the example of the strategy, or like B S, comma S S. This is another example of the strategy. So what does that mean? This is a player one strategy, and this is a player two strategy, right? Meaning that what? It means that this means that, well, if one's type is 1, then play B. If players 1's type is equal to, then play B. That's what it means. That's what this means. And similarly, we can interpret this strategy, right? If P2's type is 1, P2 plays B. If P2's type is 2, then P2 plays S. Okay. Remember, since player one is not sure about what's the type of the P2 strategy, there's no response to the P2 strategy in this situation. I mean, this is exactly what happens here in this case, right? Here in this case, where in a P1 and P2, well, the P1 is unsure about that, unsure about the P2 strategy, but P1, P2 is sure about his type. So that's why P2's strategy will consist of a tuple of the actions. When the P2's type is 1, then he will play B, and if the type is 2, then he will play S. But the P1 obviously should play anything. Like there's no like SS, BS or not, right? But here in this case, since both guys are unsure about his opponent type, then only thing that he can specify is that, okay, if itself type, like P1's type is 1 or 2, then I will play B, and so on. It does not include any kind of reaction to the P2's type, because P1 is not sure about the P2's type. Does that make sense? Okay. All right. So then we can do something like this. So we can compute the expected payoff for like every possible choices of the strategy. Like one strategy is that like P1 chooses BB and the P2 chooses BB, or the P1 chooses BB, P2 chooses BS, and we have like 16 combinations. And then for these 16 combinations, we can compute the player's 1's expected payoff, as well as we can compute the player 2's expected payoff. right? So as an exercise, let's do that. Okay. Okay. So first look at this number. All right. So how can we do that? Again, the P1 plays B when his type is this guy, right? So when his type is, this is type 1, right? And this is type 2. So 1 and 2. That's the P1's type. And this is P2's type 1 and P2's type 2. Right? So it means that this B means that what? If P1's type is 1, then I'm going to play B. So I'm going to play B. But the P1 is not sure about the P strategy. So whenever the P1's type is 1, I'm going to play B. I don't know whether the P2's type is this or this. And that's okay. And then BB, this BB means that okay. So this B, then if the type is 2, then I'm going to play B. If the type is 2, of the type of the player 1 is 2, then I'm going to play B. That's what it means. Okay? Now let's look at that. This is the, if the P2's type is 1, P2's type is 1, then I'm going to play B. Here, okay, let's look at a different number. This is type 1. And if P2's type is 1, then I'm going to play B. And this means that if the P2's type is 2, like here, then I'm going to play B. Oh, I see. So I have these choices. Okay? So if we compute the player 1's expected payoff, is that what? What's the probability that the P1's type is 1? That's 2 over 3. Okay? What is the probability that P2's type is 1? That's 1 over 2. And what is the payoff of player 1? That's 2. Okay? And then similarly, like we get this 2 over 3, 1 over 2, and 2 plus this 1 over 3, 1 over 2, and 0, because this and this plus 1 over 3, 1 over 2, 0. That's the expected payoff of player 1 when this strategy is played. Right? If we compute that, like 2 over 3 plus 2 over 3 plus 0, and that's 3 over 4. So here the answer is 3 over 4. 4 over 3. Yeah. Alright? Now what's the payoff of this guy? Well, only difference is that I have to compute the player's 2's payoff rather than player's 1's payoff. So what I can do is replace this guy with the number here, and replace this number with this, and replace this number with this, and replace this number with this. Okay? Now if we compute the player 2's expected payoff, then let's say 1 over 3, is that right? Because it is replaced by 1. Okay? Plus 0 plus 1 over 6 plus 0. And that's 1 over 2. So here the number is 1 over 2. Right? Do you want me to come up with another number? Let's say what? Let's say this. Let's compute this. Okay. All right, let's do this. So this is a SB and SB and BS, right? So if this means that, what does that mean? If the player one type is 1, then I'm going to play S. If the player one's type is 2, then I'm going to play B. Okay? Now, what does this mean? Well, if the player 2's type is 1, then I'm going to play B. If the player 2's type is 2, then I'm going to play S. And then we can compute the expected pop. Let's compute this. Okay? All right, let's compute this. So here, it's a 2 over 3 multiply 1 over 2 multiply the expected payoff would be 0 plus this guy or this guy. Do you want me to this first? 2 over 3. Oh, did I make the mistake of I don't remember that I multiplied the 1 over 3. Yeah, this may be wrong. Please correct me. Okay? All right. So I'm going to do this. 3 1 over 2 and this plus, yeah, if I'm wrong, please correct me. I cannot make sure that I'm right. In this case, 1 over 3 1 over 2 multiply 0 plus 1 over 3 1 over 2 multiply 2. Okay? All right? So that's 1 over 3, this 0 and 0, and this is 1 over 3. So it's 2 over 3. I mean, then something like that. So if you do this, you can make you can compute all these numbers, and then you can actually make a like a matrix form of the player 1 and player 2, and we have 4 strategies, and then we have a payoff like something this, and something this, right? Okay? And then probably you can compute the Nash equilibrium. What would be the Nash equilibrium? Because we have just a finite like 16 combinations of the strategies, and then we can compute the payoff, and then we can find a Nash equilibrium here. So that's the idea. Does that make sense? Okay, so I hope that you are now much clear about what will happen, how can we compute the expected payoff, and probably you can have some sense of how to compute the Nash equilibriums and so on, the Bayesian game. So we're gonna formally talk about the Bayesian game, like formally talk about the Nash equilibrium and so on. So this is nothing but a general description of what we did here and this. I mean, okay. So let's let's sort of present some more like formal description about the Bayesian game and the Nash equilibrium and so on. So Bayesian game consists of the set of players. That's what we know. So please remember this picture. Okay, when you try to understand these basic definitions of the Bayesian game and the Nash equilibrium, a set of actions, pure strategy. So here, okay. So I'm going to focus on the pure strategy. Okay, just to avoid confusion. Okay, so a set of actions, meaning that the pure strategy for each player I is Si. That's a set of available actions that I can do. So here in this above the examples, like both guys have a B and S, right? Now we have a set of types for each player, theta I, where here in this case both players are 2 types, right? Like so, set theta 1 is what? Type 1 and type 2. Here in this, okay, let's say theta 1 and theta 2. And also, this is a type of player 2. So both players have two types. Okay. which we will denote like some specific type small data I is used. A payoff function for each player I is that for example, player I's payoff is the set of actions like S1, B or S essentially here in this case, and the type of each guy. Right? Because the payoff is defined as what? As something that's okay. What would be the payoff of this Bayesian game? Well, first I need to specify the type, and then I need to specify a particular action. That's what we mean by S1 and theta 1. Right? And also I need to specify the type 2 and like type 2 and specify the action like S, for example. And that's what we mean by this, right? So here, I mean, in our example, like U1, okay, B, for example, S, type 1, let's say this is dash, type 1 dash. And that's what we mean by this is the type of the player 2. Okay, so we can compute this, right? We first determine the type and the strategy, like BS. Okay, that's how we describe the utility, and then we can find the utility of the user 1 and user 2. Does that make sense? Okay. All right. Now there is a joint probability distribution of the type. What's the probability? For example, what's the probability like type 1 of player 1 and like type 2 of player 2 and so on. Okay. So here in this case we have what? 4 combinations, right? Type 1, 1, 1 dash, type 2, 1, and 2 dash, right? Where we have 4 combinations because each player has 2 types, and that's why we denote YY, say YN, NY, and NN. We have 4 combinations. I mean, this is not correct. Yeah, like this is a. What is the probability that we have YY? What is the probability that we have YN? What is the probability we have NN? And what is the probability we have YN? That's the state. This is a joint distribution. Okay? Remember, note that this player's type may not be independent. So well, this is just a joint distribution. I'm not saying that, let's say state YY, for example. Well, probability that the player 1's type is Y and the player 1's type. Well, this happens when the type player 1's type and player types 2 are independent. But it may not be independent because we're talking about the more general setting. Right? So it's a joint distribution. But here in this example, I implicitly assume that the type of player 1 and player 2 are independent. That's why I computed something like this. I mean, in many cases it's independent. That's how the nature gives the signal, right? So the signal 1 for the player 1 and the signal 2 for the player 2, those are independent or not. So that's the issue. So generally it can be described as a joint distribution, right? All right. So in that case, we would like to note that, well, in Bayesian games, the strategy space and the payoff functions, possible types, and prior probability distribution. Prior probability distribution is the probability this is a prior probability distribution about the type that is given by the nature, and that all those things are common knowledge, meaning that each player knows that. Only thing that we assume that is that player 1 is not sure about the type, even if that prior probability distribution is given by the nature, but he does not know that probability. I mean, he knows that, but he's unsure. Yeah, sorry. He knows that, but he's unsure. Okay? Right? Then obviously the pure strategy for each player I is a mapping from the type to the action. And that's why in this case the what? The strategy of the player 1 is something like this. And what is the strategy of the player 2? Something like this. And by making as a vector, we can formally specify one strategy profile. This is a strategy of the player 1 and strategy of the player 2. That's what exactly saying there, right? For each type that I need to map an action. So for player 1's type 1, then I'm going to match the action like B. If the player 1's type is 2, then my action will be B. And similarly for the player 2, if the player 2's type is 1, then player 2 will play B. If the player 2's type is 2, then the player 2 will play B. That's what we mean by this mapping. Okay? Yeah, this is an example. And that's why in all slides I draw this. Because if you just look at the definition, it's a little bit confusing, right? Okay, what's this? So in order to make it more concrete, then I give this example, and then I sort of match the example of the strategy here with the general description of the strategy. Okay. Now recall that the players' types are drawn from some prior probability distribution. This one, I implicitly assume that in our example, those types are independent, but it's not independent, right? So what we are interested in is this probability, because we showed you earlier, in order to compute the utility or the payoff, then we need to compute this guy, meaning that remember the theta minus I means that it's a vector of all types of other guys except there's no like theta I here. So that's how I denote the theta minus I. So what I need to compute is that I need to compute probability, for example, theta 1 and theta 2. That's what we need to compute about that. Why is that? Because, in order to compute the expected payoff or the payoff, assuming that the player 1's type is 1, like for example, player 1's type is 1, what is the probability that P2, like P2 is 1, I need to compute this. P2 is 2, theta 1 is equal to 1. When the player 1's type is 1, what is the probability of the player 2's type is 1 or 2? Right? If these are independent, that's nothing but what? That's player just 2. This is just a player 2. Right? If these guys are independent. But in general, it's not independent. So we need to be able to compute this. So in earlier example, here in the logic of the computing the expected payoff, I'm using that these are independent. That's why I just multiply like 2 over 3, 1 over 2, and so on. Right? Where here in this case, we obviously need to compute this. Okay? Assuming that player 1's type is 1, then what is the probability that player 2 is 1, player 2's type is 1, and then the 2. And using this method, we can now compute the payoff. So what is the payoff of the type when the type is 1? So I'm going to compute, let's say, player 1's type is 1. Then let me compute like action B when the other guy's action is S, something like this. How can we compute the utility? So which means that, okay, when my type is 1, player 1's type is 1, and then what is the payoff of the player 1? That's what I want to expect, what I want to compute that. Then if the player 1's type is 1 and I'm playing B, where here in this case B and B. If there are other types, then I have also B. Right? And so we need to compute the sort of expected payoff of all these guys. Then what is the probability that given the player 1's type is 1, and what's the probability that player 2's type is 1, or player 2's type is 2, and so on? That's this. Right? again, if this is an independent, that's nothing but this guy. And that's how I did for this example. Okay, that's how I did this example. But in general, it should be dependent. I mean, it can be dependent. So that's why I need to use this definition. And then it's what? The utility. When I choose this action, and when I choose the other guy choose this action, when my opponent type is theta minus I, all the like vectors, and these are all the vectors, and the type is this guy, and the type is this guy. And I need to compute the expectation for all other possible choices of the types except for me. Does that make sense? Yeah. Well, when you first take a look at this thing, it's a little bit confusing. And that's why I spend a lot of time on explaining and providing the examples of like this case and another case before describing the general description. So due to this region, we need to compute this guy, and given the joint probability distribution, how can we compute this guy? I mean, even if those types, I mean, the players' types are dependent, well, we can use the base rule, right? I mean, for example, if this is given, like this is given, everything is given, like this is given, then obviously you can compute like what is the probability B given A, what is the probability A given B. You can compute that, right? That's basically, we need to use the base rule. And that's why, I mean, in some sense, that's why this game is called the Bayesian game. Okay? All right? So when the types are finite, then, well, we can use the like sigma. When the types are not finite, then we can use the density function and the integral. That's pretty much like undergraduate level algebra. Okay. So going back to this thing, can you compute the Nash equilibrium? Well, you can compute the Nash equilibrium by making the table like this. Right? The basic, well, of course you can make all these tables, and then you can find a Nash equilibrium. And also what you can do is that you can sort of compute the best response function. So you can, in order to check this thing, okay, is this a Nash equilibrium? Well, first you need to check, well, for BS, player 2's, is player 1's BB a best response? You can check that. And similarly for P1's BB, is P2's BS a best response? You can do that. You can do that. But it's not a simple structure. But think about that. Right? Because, well, yeah, please think about that. You can do similarly apply the same like best response based definition of the Nash equilibrium in order to check whether this point is the Nash equilibrium or not. Can you do that? How can we check whether we check where P2's this strategy is the best response? How can we check that? Right? You need to think about that. Well, we did a similar thing for a simpler game. Like for example, I mean here in this case, the pi 1 and pi 2 are given. So well, like for example here, for the B, then we check that, well, B comma A is the best response for 1. Now, but here in this case, P2 is unsure about the P2's type, but the P2 is sure about that. So that's why we have just like triple thing, right? But we have now, we are talking about like B, B, S, B, and so on. So, you know, checking strategy is a little bit complicated, right? Okay? All right? but I'm sure that you can do that using the definition of that. So in order to formally describe the sort of the Bayesian Nash equilibrium definition, strategy profile, you know what the strategy profile is, right? This is a strategy profile. And an example of the strategy profile. This is a strategy profile. Is a pure strategy Bayesian Nash equilibrium or Bayes Nash equilibrium for all players I, and for all type we need to satisfy where the strategy Si for the type I should be the argmax of all other strategies. Okay, so the type is given, okay, here, and we need to check whether this Si, when the type is theta I, is the best response with respect to the expected payoff, right? Right? I mean, this is what happens in the non-finite case. So, in this, I mean, Nash equilibrium definition, which follows our intuition, pretty much follows our intuition. But it's a little bit confusing there for all like type I, and we're looking at this one, right? So suppose that you claim, like for example, BS SS is a Nash equilibrium. Suppose that you claim that. How can you prove that? Okay, let's use this example. Let's use this example. So it means that when the player's type is 1, I'm going to play B. When the player's type is 2, I'm going to play B. When the player's 2's type is 1, I'm going to play B. When the player's 2's type is 2, I'm going to play S. I claim that, I mean, if this is a Nash equilibrium, I claim that this is a Nash equilibrium, and what it has to satisfy is this. So what is this? For example, when the player I's type is 1, and what is my action? My action is B, right? So like S1 theta 1 is equal to type 1, then my strategy is B in this case. And that should be the argmax of all other strategies. Essentially, we need to compare B and S, right? Of this expected payoff for a given choice of other strategies, like SI. Okay? So for a given type, and then I'm choosing B, and I need to compute the expected payoff of others. And then we can check whether this is the best response or not. So the best response can be checked per type, as well as for given that type, the strategy. Right? Per type and strategy. Because like S1's strategy, when the type is 2, and here in this case also B. Right? I need to check whether this is the best response. Player 2's type, when the player's 2 type is 1, is here in this KB. I need to check whether this is also the best response. I need to check whether player's type is 2 is S. I need to check whether this is also best response. So but the best response checking should be done like 4 times. 4 cases. Why is that? Because, well, I have just as 2 strategy B and S, but since the type, I have 2 types. So all the combinations can make happen for the 4 cases. That's why we have this. This is okay, yeah. So some people, this is a kind of expanded game, meaning that, well, each player I's space of the pure strategy is expanded depending on the type. Here in this case, I originally have just B and S. Well, if this game is not a Bayesian game, but it's expanded to like what? The 4 cases. What is the strategy of the type is 1? What is the strategy of the type is 2? And so on. I'm sort of expanding my strategy spaces. And that's why I need to check this guy. right? Okay, and that's why, I mean, this is exactly the same as the, okay, my strategy can be a form of the 4 actions depending on the type of the player 1 and player 2. All right. Okay, there's some existence theorem. Finite incomplete information Bayesian game, then, well, pure strategy Nash equilibrium may or may not exist. But as we proved that for the normal finite normal form game, a mixed strategy Bayesian Nash equilibrium always exists. I mean, that's pretty much an extension of the previous result, right? I mean, we just expand the strategy spaces. For the continuous case, well, under some conditions of the beautiful, I mean, under some beautiful conditions of the strategy sets and the type set, like compact, for example, and the payoff functions are continuous and concave, then pure strategy Bayesian naturally can exist. I'm not going to go to the details about this and why that happens, but this theorem essentially is a simple extension of what we have talked, why we have discussed for the non-Bayesian game setting, because it's just an expansion. All right? Okay? So what you need to do as a homework is that we're going to apply this Bayesian game setting for the Carnot duopoly situation. Where in the Carnot duopoly, if you remember that there are 2 firms, both produce at a constant marginal cost, and there's a demand, price, as in the usual Carnot game, and the firm 1 has a marginal cost which is equal to C, which is a common knowledge, but the firm 2's marginal cost is a private information, meaning that firm 1 is not sure about the marginal cost of the firm 2, and that is like CL and the CH with some probability, where this thing, and then what happens to the Bayesian Nash equilibrium in that case? Do you understand the setting of the problem, right? And how can we do that? So this is a good example to make exercise for the Bayesian game. With continuous strategy space. Okay? All right. Let's summarize the lecture. So now we talked about the Bayesian game. So what is a Bayesian game? Well, there exists a private information essentially. So what is a private information? It's a payoff structure. Essentially. Well, in a Carnot duopoly, the fact that we have a different marginal cost means that it's a different payoff structure, or the unsure payoff structure. Okay, so it is formulated by introducing a notion of type of each player. Okay, so player 1, player 2, player n. Each guy has a type from theta 1 to theta, let's say, something. Okay. Now the framework is that the nature gives a signal to each players about its own type. Like okay, I'm going to give you your type. I'm going to give you P2's type. I'm going to give the P3's type. I'm going to give the Pn's type. So the Pn knows the type that is given by the nature, but he is unsure about what other guy's type. That's the setting. Meaning that P1 is unsure about the payoff structure, payoff function of other players. Now remember, there could be other information that can be private, like a number of players, or strategy space of other guys. Well, we don't assume that this is not this is unknown. We assume that this is known. Only thing that is unknown is a payoff structure, or kind of a probabilistic conjecture about other guys' payoff, and that is introduced by that is essentially can be explained or formulated by introducing a type of each player, right? And then pretty much the other things like Nash equilibrium and how can we analyze the game, it just follows from the earlier like extending the earlier definitions of the Nash equilibrium and everything and so on, like existence theorems and so on, by introducing this probability distribution, I'm saying. So remember the types probability distribution theta 1 to theta n. There is a prior joint distribution. It's not necessarily may not independent. So in this case, we need to compute the theta minus I given theta I in order to compute the expected payoff. And that's where the base rule comes from. Given this joint distribution, we can compute that. And that is why this is called the Bayesian game. Okay? Alright, I hope that you have a clear understanding about the Bayesian game, and probably doing some exercise of the homework that I assigned, then your understanding about the Bayesian game will become more clear. Okay? Alright, I'll see you in the next lecture.